All right, hello everyone. This is going to be the key to your Unit 2 study guide. We're going to start with the terms and graphing, so let's just jump right into it. Number one is asking us to describe the difference between distance and displacement, and more specifically, what are some common units, and basically, what do they measure? So let's start here. Both distance and displacement measure how far an object is or how far it has traveled. So how far an object is from, I'll say, is from a location. So if we're going and we're talking about this, of how far an object is from a location, the main important is that displacement, which we denote with a delta x in physics, has a direction associated with it. So if we are talking about the difference, distance really is just how far. I'm 1 mile away, but it's a circle, as opposed to displacement can be something like 1 mile north. Of some common units for either one, if we are talking about it, the SI unit is meters of just how far, but it also could be kilometers, it could be miles, it could be just anything that has a distance or, again, tells how far. Number two is talking about myself and me sitting at NARICS and realizing that it was time to go home. On the way home, I eventually figured out that I left my items here at school, so instead I turn around and then go back. The way I want you to think of it is distance and displacement by itself. Distance is just the total ground covered. If you run, if you walk, how much gas you've used, it's the total ground. As opposed to displacement, I always tell my students it's the distance away from your starting point. So if I start at NARICS, here, we'll draw NARICS there, and I travel 2 miles there, 2 miles back, and then the total 5 miles to my house over here. Well, then by itself, the total, let's start out with distance. The total distance is the entire thing of how much gas have I used, how much miles has my car felt. Of the entire thing, you notice I have 2 miles there, 2 miles back to grab my stuff, and then 5 miles. So my total distance has to be 9 miles traveled, as opposed to my total displacement is just the distance away from my starting point. I started at NARICS, I ended at my house, so immediately you notice that the displacement between them is only 5 miles. That's the difference. Okay, let's talk about some variables. And I'm asking by itself, what are some common scalar and what are some common vector variables? Let's first remember that vectors have direction. That is the main difference between them. Some scalar variables are things that don't have direction. Things like time, mass, volume. They're different variables that there is absolutely no way in which direction can be associated with them. As opposed to vectors are things that do have a direction. So they are things like velocity, like acceleration, like force, that they're all different ways in which you can immediately understand that the direction makes a big, big difference. Along the same lines, I'm asking, what's the importance of vectors? Well, vectors, S, with direction, they give us more info. I like to go and describe to my students again that the way I go and I really talk about it is that if we're going, and I think I've used this analogy before, if we're playing hide and seek and you go and you tell me, oh, I'm 2 miles away, that's still 2 miles I have to cover to try and find you. But if you tell me that it's 2 miles north, 2 miles south, 2 miles east, that's easier for me to figure out. So I'm asking by itself of if I was going to travel 3.1 kilometers to the west, how in physics do we represent, vectors numerically? And the way that we do it is with a positive or a negative. If we travel west, basically we went and we called north positive, east positive, south is negative, and west is negative. The idea, it's the same as in math. We're trying to set directions and values to each. That's it. So again, the main difference between speed and velocity and some common units is that velocity is a vector. Velocity has a direction associated with it. But the units for them, speeds and velocities, are always in distances over times. So meters per second is the most common, but we've also used kilometers per hour, miles per hour. Things like that are all how fast that they are traveling. And lastly, describe an acceleration or an example of an object that has a fast acceleration. What are some common units of it? Just means anything that increases its velocity or decreases its velocity very, very quickly. So myself, what am I feeling? I'm going to go and I'm going to say something like a rocket. In order to in order to reach escape velocity, that thing has to have a really, really, really fast acceleration, which is why you see those burners down at the bottoms. But some common units, accelerations are always with a squared time value. So meters per second squared is the most common, but again, kilometers per hour squared is also very, very widely used of anything with a squared time. All right, now it's time for graphing. So we have analyzed the following graph and use it for the following questions. Of the three examples presented between A, B, and C, which letter has the fastest velocity? And how do I know? Well, immediately I know that it is swimmer A because the slope of a position time graph tells us how fast it is traveling. Therefore, with A having a steeper slope than the others, I know that A immediately is traveling the fastest. Look at swimmer B. Does the velocity of their swim ever change? And again, nope. Of a straight line by itself, this is a constant velocity. And I know that since it's constant, it's not going to change. All right. It went and got cut off, so I'm not going to be able to describe it here. But my next question is to briefly describe an explanation for swimmer C. Swimmer C, you notice the main purpose and the main reason why I want you to be able to describe an explanation is because if we look at this graph, this portion right here on the graph, that means that the swimmer is not moving. So I would say something like the swimmer went and traveled 400 meters in 10 minutes. Of course, traveling 400 meters is not easy, so they got tired. They waited for an additional 10 minutes just to catch their breath, and then swam faster at the end with a steeper slope up until 30 minutes. Something of the sort. All right, keep on going. Analyze the following graph and answer the questions. So first it goes and it asks me, what sections have a positive displacement and what sections have a negative displacement? All that this is it's asking whether or not it has a positive or a negative slope. So immediately represent a positive displacement. Positive for me is going to be positive equals 1 and 5. And then a negative is just 3. Of 2 and 4 are no slope. That's 0. Now, if that object is not moving, so I wouldn't really count it as a displacement because displacement, again, is how far. So that's what I would say. Between the sections of 1 and 3, which section is traveling at a greater velocity? Well, here, I can see that it's 3, and let's really describe as to why. It's whichever one has the steeper slope is really what it is. So the way that I like to go and talk about it is that 1 and 3 are positive and negative. They're traveling in different directions, but 3 is traveling faster. And let me show you why. 3 by itself, if I go and I just plot, well, 3 travels in 4 seconds, and it travels 4 meters. So 3 will travel 4 meters in 4 seconds. As opposed to 1, if I do the exact same thing, if it goes 4 meters, well, 1 traveled 4 meters in 6 seconds. So in 6 seconds. Since 1 is going to take longer, therefore it's traveling slower, and 3 has a higher velocity. Okay, 9, we are going and we are looking at a velocity versus time graph. First, I have to ask you, what does the slope of a velocity time graph tell us? Let's start out. Slope is defined as the change in y over the change in x for any. For a velocity, that means that we have the change in velocity over the change in time. Therefore, since I replaced my labels, the change in velocity over change in time has a name. That's the acceleration of the object. So acceleration is 100% the slope of a velocity time graph. So now we go on to B. At what time period is the object experiencing the greatest rate of acceleration? And how do we know? Well, oh my goodness. It is from right here to right there. So I would say from 3 to 4 seconds, that object is experiencing the greatest rate of acceleration because the slope is the steepest. The steeper the slope, the greater the rate of acceleration. And last but not least, is there ever a time period on this graph in which the object is not moving? Explaining my answer, I would have to have a horizontal line right here somewhere on the 0. Since I do not have a horizontal line anywhere on 0, then immediately I say no, that there is not a time in which the object is not moving. And then D, what is the motion exhibited past 7 seconds? How do we get a curve? The only way that you can get a curve on a velocity versus time graph is if we have a changing acceleration. So, and changing acceleration is just if someone is putting their foot really far on the gas and then letting out and then a little bit more. It's changing over a function of time. So, you have a changing acceleration. All right. It is time to actually go and to graph and to figure it out. So I'm going to try to do it here, but it is not going to be simple for me. So I'm first going to start by zooming way out. Hopefully that works for everyone. And again, I'll be zooming back in and trying to see, but it's not perfect on an iPad as I'm doing this. So I'm hoping to graph this specific set of data. The first thing that I have to talk about is, well, I need to know what I need to add to a graph. So let's start out there. In order to add items to a graph by itself has to have three specific things. That is a title, that is by itself, axis labels, and that is an even scale. So if I look at my graph, let's first start with axis labels. I know that I am graphing a distance versus time graph. So time has to go on my x-axis, so time in seconds, and then distance has to go on my y. And is it in, oh, I messed up. I thought it was kilometers, meaning that is not seconds. That is hours, and then my distance is in kilometers. If I write a title for a graph always must restate my variables. So my title is just going to be distance versus time. I need to then decide a even scale, and here the easiest scale for myself I think it works out nicely if I just quickly check. I think going up by ones is perfectly fine here because I'm going to use the majority of my graph. So I'm going to start first. You always start every single graph at 0, 0. And me, I'm a lazy person. I go and cut corners when I get to it. So I'm going up by ones. But I don't want to write every single time, so I'm skipping one. But again, I have an even scale. Each number is the exact same. And then I do the same thing over here. I'm going to go 2, 4, 6, 12, 14, 16, 18. Just making sure that my graph stays the same as time increases. 28. Is that right? Okay. So after we have gotten this, we've got our 3. It is time to plot. So I'm going to zoom way, way, way out. And I know that I can see it. Yours is a little bit cut off, but we choose first our x-axis and then our y. So my first is 3.12 and 2.2. So I go to 2.2 and 3.12 is about there. 4.8, 5.91, 4.8, 5.91. And again, as I am doing this, I am not purposefully choosing like exactly where each point is. I'm estimating. I'm saying, okay, I can find 8, but 9.75, well, that's about 2/3 up from there. Then 10.5 and 12. Ooh, that's a change in data. Okay. 12.3, 14.68, so 12.3, 14.68, I'll put there, and 14.6, and 18.09, which is basically just 18. So 14.6 and 18.09. It's about there. So again, my points use the majority of my graph, but now you can see if I zoom in again, that by itself, it's much, much, much nicer. And I have a line going through. So now I need to make a line of best fit and solve for my slope. I'm going to cheat. You should be using a straight edge, but I can go and I can insert a shape. So I'm going to insert a arrow where I think my line of best fit is going to go. Now, mind you, a line of best fit is a singular line. I am not going through. It needs to go down a little bit. I'm not going through, and my line of best fit is not going to be like this, line that goes and jumps from point to point. It is a straight line all the way through, and I'm kind of happy with it as it is right now. So I'm just going to save it, and let's go. And next, I have to choose my slope. So once I have drawn my line of best fit, I need to start searching for intersections or points that are easy for me to read with such a perfect line, though, I don't think I'm going to get any intersection. Oh, that's close enough for me to count. All right, so I'm going to choose 2 points. Let's do a nice magenta. I'm going to go here, and do I have another intersection? I'm going to count that one. So I find 2 points on my line of best fit, and I choose my x and y coordinates. And what I'm hoping to do, so let's go here. My x coordinate here is 20, comma, y coordinate is 23. And over here is 14, comma, 16. Done. So I have my x and y coordinates. In order to solve for slope, I always take y2 minus y1 over x2 minus x1. If I'm trying to solve for this, though, I need to decide what's my first point, what's my second point. My first point is always the one that is closer on the x-axis, the one that has a smaller x value. So that is point 1. This is point 2. So I have x1, comma, y1 here, and I have x2, comma, y2 here. So if I'm trying to do y2, I would plug in, then for my slope, 23, and here, this is a number now, so it needs a unit. So my y-axis is kilometers. I would do 23 kilometers, and I would minus of y1, 16 kilometers, divided by x2, so 20 hours, minus x1, 14 hours is my slope. So then I would go and I would look of my slope is going to be equal to, this is 23 minus 16 is 7 kilometers over 6 hours. But I do not leave it as a fraction. I'm going to come down here and 7 over 6. I put it into my calculator. I get 1.16 repeating. And here's the beauty of it. We do not have to take sig figs off a slope because it's not a measurement. Therefore, we just round it to something reasonable. I'm going to do 1.17. And again, units are kilometers per hour. So there's my slope. And that's what I would go and solve for up here. But last but not least, let's plug it into slope-intercept form. Here, slope-intercept form in physics is so much nicer than in math because you're not solving anything. You're just creating a new equation. Based off of my graph, my y here is always just my y-axis of m is your slope, x is your x-axis, and then finally b is your y-intercept. So if I am plugging this in by itself, I would start with my y-axis. Here, let me change color back to purple. My y-axis is distance. So I would write distance equals my slope, which is 1.17 kilometers per hour, multiplied by the time, my x-axis, plus my y-intercept. But here, my y-intercept is 0. It could also be like wherever, it's basically just wherever your line crosses over the y-axis. So here, I would put plus 0 kilometers. And that is my final slope-intercept form. Well, again, thank you. Let me know if you have any questions. And that's the end.